Hello everyone, I hope you and your family are doing well. I am Gyanendra Kumarsa. I am currently doing my PhD in University of Rostock. As I have already explained in my previous videos that I am going to make a series of videos which will help you understand cascaded control design for DC-DC converters. This is last video in the series, and here we would like to validate our proposed outer voltage control loop in Cascade with the inner current control loop using Matlab Simulink environment. So here we have listed the 5 lessons which I had planned to prepare and upload to YouTube. So the main objective of all these 5 lessons are to help you understand the cascaded operation of inner current control loop and outer voltage control loop for DC-DC converters. So I have already finished with the 4 videos and you can find that in my channel. In the lesson 1 and lesson 2, we learned how we can design inner current control loop in both continuous and discrete time domain. And we also learned some basics about designing the controls in continuous and discrete time domain. For example, obtaining the discrete plant model, obtaining the continuous time domain plant models. So lesson 1 and lesson 2 were about theory. And then we used the theory explained in lesson 1 and lesson 2 to design our outer voltage control loop in both continuous and discrete time domains. So from lesson 1 to lesson 3, this was about the theory. Oops. Okay. And in lesson 4, we basically validate our proposed inner current control loop using Matlab Simulink environment. So this was about simulation, and here we saw the performance of our proposed inner current control loop for buck converter, boost converter, and buck boost converter. And we would like to do the same for this lesson, where we want to validate our proposed outer voltage control loop in cascade with the inner current control loop. So this is also about simulation and implementation. Okay. And so this is the major focus for this video. So if you have not watched this lesson 1 to lesson 4, then I highly recommend you to first watch these lessons and then continue watching this last lesson, because information given in all 4 lessons, all first 4 lessons are going to be used here. Okay. So these are the main topics which we are going to cover in this video. So in the first part, we would see the structure of the proposed cascaded control loops. So this is just to give overview of our first 3 lessons. And then we would see our Simulink model. So we would like to go through our Matlab script and then Simulink model, and we will understand what is used there. And then we would like to see the results. So for results, we have like step responses and then the failure analysis. So this is in time domain. And then we would like to also see the importance of anti-winding. So in my 4th video, I mentioned that anti-winding is very important. So especially this is very important when you use saturation in your control block, and then our control signals are saturated. So in that case, our integrator integrates the wrong value. So we need anti-winding for integrators, and we will see the importance of that. And at the end, we would like to see the closed loop command tracking plots. So this is your frequency domain plot. Okay, so okay, let's move forward. So I have already prepared the model. So it took me a quite long period of time, more than 3 days to prepare everything. So you can go to this link. You can go to this link now, and you can paste it in Google, and then you would see something like this. So here you can see there are different Matlab version Simulink model. So I have the MATLAB 2020B. So, but you may not have the higher version. So I have tried to get the model for previous versions also. And then we have some Fft analysis. This will help you to get the body plots. These are the parameters for simulation. And then this is to do your analysis of your step response and body plots in using analytical methods. So we do not do simulations, but you can get this the behavior, how your control should behave, yeah, without doing any simulation. So this is just to check things. So let's download this. Okay, so now it's downloaded. So let's go to its location and then you can extract this. Let's extract here itself. And then you can basically open the MATLAB and go to this location. So let's open the MATLAB. So this is your MATLAB. Then you copy and paste the location. Okay. Then we have these models. So this is the same place where we extracted the files. And this is our parameter list. So here you can see different settings for your converter design. Then so yeah, we will go through these in the slides. So here you can see the PI tuning expressions, then for command tracking plots, and then step response, there are some settings. So we will go through this in the presentation. And then I use MATLAB 2020B. So I would like to open this. So whichever MATLAB version you have in your laptop, you can open that MATLAB version, and I hope it works fine with your MATLAB version. So I have not tested with the lower version MATLAB, but I think you can do that. So it's taking a long time to open. Yeah, now it's there. Okay, so once you open the model, it looks like this. So this is the very main page. And here you can see some one scope. So this is scope. You can see your average output voltage and currents for all three topologies. And then we have here load resistance. So this is for load implementation step in the load. This is for our V out reference. And then this is for short circuit implementation. So we would like to also do the failure analysis for our control. And of course, you can open these blocks and then you find several things. Okay, so we will go through these in presentation. So I have already prepared, taken the screenshot of those parts, and then let's explain it here. So this is just a summary of our lesson 1 to lesson 3. So if you have already watched the lesson 3, you at the end you would see this picture. So from this picture, what we have is, this is our so let's choose another color, blue. So from here to here, we have our outer voltage control loop. And then from here to here, we have our inner current control loop. Okay. And as I explained in my my third video, that this we can use for safety of our device. So this is going to be used for protection. So here what we try to do is, if we have some failure cases, we would like to limit our reference inductor current so that the high currents does not flow into our DC-DC converter. Okay, so I would assume you are already familiar with this circuit diagram. And if you're not, then you can watch the third video of this lesson. So here you can see there are 3 main parameters. Okay, so the first parameter is your A, the second parameter is your B, and the third parameter is your D. So you can see the A parameter here, the B parameter here, and then D parameter here. Okay, so these A, B's and the D parameter changes with your topology. So if for buck converter it can be different, for boost converter it can be different, and then for buck boost it can be different. So here I have already listed these parameters. So this A, B, and D, and if you have watched the first three videos, you would know that how these expressions are obtained. But I would like to mention that in the third video, we also mentioned that you can compute this capital D using 1 minus T, but we do not want to use it. We don't use this because it introduces the coupling between the high the high frequency I would say the faster current control loop and the slower inner current slower outer voltage control loop. So it introduces uh, the interaction between them, and hence it makes things unstable, or it makes things worse, that the performance will be bad. So you can also do that in Simulink model, which I have already downloaded, and then you can also see how it looks like. Okay, so this was about uh, the the control structure, and now of course you would need to tune the controller. So then we have to tune the PI controller. So this is again the summary of our first three lessons. So this ICC means our inner current control loop in continuous time domain, and this is inner current control loop in our discrete time domain, and how you can tune the KP and KI. And similarly, we have for outer voltage control loop in continuous time domain, and then tuning for outer voltage control loop in discrete time domain. So these are the expressions for KP and KI, which you can use for tuning, and the rest all parameters which is needed to tune the KP and KI are mentioned in the below. Okay, and in continuous time domain, we implement our PI controller like in the image shown above. So in continuous time domain, we use 1 over S for integration, and in discrete time domain, we use KIT into by 1 minus Z power minus 1 as our integrator gain, our integrator implementation. Okay. Okay. So as I already mentioned, that you can also use different expressions for integrator, but at the end, the procedure is anyway the same for tuning the PI controller, so that would not make much difference. It will just change our KP and KI expressions for discrete time implementation. Let's go forward. Okay, so that was about the theory. Now let's see our Simulink Simulink model and the Matlab script. So the similar Matlab script we saw in our in the fourth video, where we validated our inner current control loop. So these parameters are same, and here there is a change, that now this time, since there are a lot of control blocks we are implementing, we have outer voltage control loop for all the converters, so there are a lot of computations going. So this time I try to keep this as 200 times less than switching time period. So this is our Simulink sample time, and in the fourth video I had taken it as 500 times less than the switching time period, but that was maybe fine for simulation because there were not much computation doing. But this time if I make 500 times less, then it's very slow because it has to do a lot of computation. So just to make simulations a little faster, I have chosen this as 200 times less, and which is also fine. And then we have these are again the additional parameters. So where we for designing our capacitors, we have chosen the delta VC. So this is our delta VC, and I have chosen some different values. So for buck converter, I choose 1 voltage as a ripple, and for boost and buck boost, I choose 10 volt as a ripple. You are free to choose the voltage ripple according to your design. But so these voltage ripples will change your capacitance value, and then it is going to change your PI gain also. Okay. Yeah. So now then this is same. The duty cycle computation is same. Then we, so until here until this inductance calculation is the same. So we have this additional expression for capacitor value computation. So this is for capacitance, capacitor value calculation. So you can use any equations which you like to tune for capacitor. So as I mentioned in my first video, we do not focus on designing. We want to focus on control. So, but for simulation, we need some values. So we compute them like this. And these are our internal resistance for the inductor and the capacitor. So this is about the parameter settings of the converters. And then for tuning the inner current control loop. So for tuning the inner current control loop, we already saw the Kp and Ki expression. So we have tuning in continuous time domain. We have tuning in discrete time domain. And in continuous time domain, we already saw Kp is equal to basically omega Br into L. And Ki is equal to R over L into Kp. So which you can also see from here. So for all converters, you can see these expressions. And for tuning buck converter, for sure, you have to use the buck converter parameter. And for tuning the boost converter, you have to use the boost converter parameter. So for tuning the inner current control loop in discrete time domain, again, you can see the expression. So it is like T over tau over R. Tau is equal to your L over R. And then your Kp is equal to e power minus T over tau into 1 minus e power omega Br T over K. And then your Ki, similarly, you can find it's like this. Okay, so yeah, so this is our the tuning expressions for Kp and Ki. So which you could also see on the previous slides. So this is for our outer voltage controllers PI tuning, and as we also saw in the third video that we cannot do pole zero cancellation for tuning our outer voltage control loop. So we will have a second order system for outer voltage controller as a closed loop transfer function. So we will have two eigenvalues. And we also mentioned that our outer voltage control loop is slower compared to our inner current control loop. So that is why, and that we can do by tuning the bandwidth of the outer voltage control loop at least 10 times less than inner current control loop. So we mentioned that F2 is approximately close to FBR. So it will never be FBR, but it will be close to FBR. And this is your FBR outer voltage control loop. And this outer voltage control loop you can choose as like the BR of inner current control loop at least 10 times less than or equal to, yeah, so less than or equal to 10 times the bandwidth of the inner current control loop. Okay, so here I have chosen 10 times less, and we will also see the Bode plots for 5 times less. So just to show you different for different bandwidth, I have given the results, and here F1 is I have taken always as F2 over 10. Okay, and then we get the omega 1, omega 2, and for Kp and Ki tuning, so here this is in continuous time domain. So Kp is your omega 1 plus omega 2 into C, and Ki is your omega 1 omega 2 into C. So in discrete time domain, tuning in discrete time domain, we have to use different formula, and we know that these are our poles in discrete time domain. So Zp1 and Zp2, so which are related with omega 1 and omega 2. And then we can find the expressions like this. So Kpi is equal to 1 minus Zp1 minus Zp2 into C over T. And del is equal to 1 minus Zp1 multiplied with Zp2 into C over T into Kpi. And our Kp gain is equal to Kpi into del and our Ki gain is equal to Kpi into 1 minus del over P. So these are the PI tuning expressions. So I just try to write it here so that you feel confident that the same expressions are used for tuning our Kp and Ki gain for the controllers. Okay, so now as I mentioned that we would like to see the step response and the command tracking plot. And so how do we choose from the MATLAB script? So I try to make everything automated. So you just have to change one variable. So this is the variable you should change. So if you make it 0, which you can see here, so we only initialize and then we want to get the step responses. If you make this 1, then what happens? The Simulink model will run from this MATLAB script. And yeah, so you can see the run the model multiple times automatically and save the data, and then at the end get the command tracking plot. Okay, so and these are the settings for your step time response. So for step time response, I try to make the runtime 1.4 second, and this is for your body plot. So after else, you have the body plot stuff, and when we choose this this command tracking plot on as 1, then we have this frequency, and for the so and for this length of frequency range, the simulation will run again and again, which you can see here. So this is a command which will run the simulation, and then we will sample these the voltages, and after sampling the voltages, we will basically do the Fft analysis on it. So if you have watched the 4th video, you would know that the Fft analysis we use to get the magnitude and the phase of the body plot. Yeah, so here we get the magnitude and phase for all converters. So for buck converter, boost converter, and buck boost converter, and at the end, what we do is we have some commands after that. So this is to plot your command tracking data. Okay. Okay, so this is how we can do the step response and the command tracking plot. So that was about the Simulink MATLAB script. Now let's talk about our Simulink model. So this is the same page which we saw after opening the MATLAB Simulink model. So here we have the load resistance. So this one we use to simulate our various load conditions. So we give step in the load. So we try to overload the converter also and see how if our converter is safe. This is to generate our reference voltage. Okay, so this we would like to generate the reference, and so in the step time in the step time response, basically this will be 0, and we give just a step value in the as a reference voltage. And when we want to get the body plot, we would like to give the sign reference, like some harmonics we would like to add. So it will have some DC, and then it will have some AC. And the magnitude of AC is 10 times the magnitude of the DC. So it will be like this, 2 pi F into T. And we change, and what F range you saw. So it's basically this value. So it's not the F range, it's just the one value of the F range at a time. Okay, so like let's say F range is your for example 1257 hertz. Then your F value initially will be 1. Then it will run the model and save the value, and then the next time the model is running, it will be 2, and then it will be 5. Yeah, so it will keep on changing and run the model, save the data, then again change the value of F according to F range, and then it will run the model again and again. Yeah, so it will run the model again and again. This value is, and so F range is equal to the int value of F value is equal to the F range. That you can understand from the MATLAB script if you go through it. Okay, and then this is for implementing the fault analysis. So I mean the fault on the load side. So we would like to do short circuit on the output voltage and see if our converter and our controller is operating safely or not. And we have on this big scope. So this is to see our V out average. So this is to see our V out average and then I out average for all converters. So which we will also see. And here we have control for all these three topologies. So we have for buck converter, boost converter, and buck boost converter. So let's open this part. So once we open this buck converter, okay, so before we go there, so this is our parameter settings, and this is the same settings as our fourth video, so where we tested our inner current control loop. Okay, so when we open that buck converter block, which you can also read from on the top, okay, so you can read it from here also where we are actually. So again we have some scopes to see the results, and you can notice that I use underscore s. So let's say something abc underscore s is for continuous time domain. And if we have something like abcd underscore z, this is for your discrete time domain. Okay. So there we have some scopes here. So the upper one scope is for continuous time domain, and the lower scope is for your discrete time domain. And you can open and you can see various parameters here. For example, you can see the output voltage, you can see the output current, you can see inductor current, and then you can see your duty cycle and the carrier waveform. So this is our, so if let's see first the continuous time domain control implementation. So this is our hardware. So inside this we have our electric circuit, which we will see in the next slide. Then we have this sample signal. So these are our sampled signal. And then these sample signals are used in the control. So this is our inner current control loop, and this is our outer voltage control loop. And of course, they are in continuous time domain. Okay. And so we already saw the structure of inner current control loop and outer voltage control loop. So so the main important thing is how your A, B, and D values are computed. So here A, you can see it is Vs average. B is your minus V naught average, and then D is basically, you can see here, D is equal to 1. And then we have the feedback. So here there are important things to note are these things. So this is our anti-winding. So this is our anti-winding. So what it does is, if the output of saturation block and then input of saturation block are not the same, then it gives 0 to integrator, and so then basically the input of the integrator is disabled, which we will also see in the next slide. So this is our very important part, and this is what is used for protection. So here we would like to saturate our inductor current value, inductor current reference value, so that our converter never runs into unstable or very high current operating mode. Okay, because inductors are rated for some current, so for sure we should not exceed, we should not draw more, we should not make more current flow through the inductor, especially during the faulty and overload conditions. Okay, so you can see these A, B, and D expressions. So if you also see in the discrete time domain, you can also see it's like the Vs average. So here basically we do the sample. So I can say AK is equal to your Vk, and then B of K is equal to minus V naught of K, and then D is of course equal to 1 here. So why I say K? Because we use double sampling, and this is a sample and hold block which you can find in Matlab, and this basically sample things. So let's say this is our carrier waveform, and we sample the signals at the upper and the lower carrier wave, upper and the lower carrier extremes. Okay, so yeah. So you can see carrier waveform here, and so this is the same graph, and here we sample the signals only at the extreme. So in one switching time period, we basically sample two signals, and hence it is called double sampling. So we do not do actual mean here, we just sample the signal and just feed it to the control. So that's the difference in discrete time domain and continuous time domain mean calculation. Okay, so now we should decide what is the upper and lower limit for the inductor reference current. Okay, so how we find that? So then let's see. So I mean this block, you can see this block. So this block basically finds the suitable maximum limit for your inductor average current saturation block. Okay, so let's see that block. So let's first see the circuit diagrams and then controls. So this is our circuit diagram for buck converter, and you can clearly see it is a buck converter, and then parameters are set according to our parameters in the Matlab script. So this is the same R load which we saw in the main Simulink page, and here we can change the R load value. And this is for implementing short circuit on the DC-DC converter. So if this variable gets 1, it means we have a short circuit on the on the load side. Okay, and then we have if you open the inner current control loop in continuous time domain, then you would see this block. If you open the inner current control loop in discrete time domain, you would see this block. So you can see they both look similar. The only difference is that the PI implementation. So for continuous time domain, we use 1 over S as integrator, and in discrete time domain, we use so this, if you rearrange this, you can see that it is equal to this. Okay, so just the difference is your integrator implementation. And the same thing, this is our outer voltage controller in continuous time domain, and this is our outer voltage controller in discrete time domain. Okay, and you can see the tuning of the value of Kp and Ki. So underscore S is used for continuous time domain, underscore Z is used for discrete time domain, which you can also notice here. This was about circuit diagram and control blocks. And now let's open this this block which we discussed before. So this is for protection. Okay, so you can also see the title which says protection during overload and short circuit conditions. So here there are different settings. So there are many ways you can protect this. You can protect your device. So let's say this is your converter. This is your DC to DC converter, and this is your load. And you have a source here. So it may happen that the load draws more power, right? So if the load draws more power, then your converter, so there will be more power flow through the DC-DC converter. So it can be greater than the rated power for DC-DC converter, and hence your semiconductor devices or inductors or capacitor, they could fail. So we need to also limit the power. Okay, so we need to limit the output power. So that's one objective. And you know that during short circuit, the currents can also go very high, right? When we have a short circuit here, then the currents can go a very high value. So and during short circuit, you know the power drawn is if it's a solid short circuit, that means there is no output voltage, then the power is 0. So power will be very minimal during the short circuit condition. The output power will be very minimal. So this power limitation will not help us all the time. So what we should have is our current limitation also. So our output current limitation is also needed. So we need to change our the IL average maximum value based on these two conditions. And there is one more condition. So that one more condition is not necessary for this buck converter, but that is very important for boost and buck boost converter to limit the inductor. So basically, we should not allow more current flow through the inductor than its rated current value. Okay, so yes, so basically IL average star should be less than or equal to your IL average maximum for the inductor. Okay, so this is also one condition which we will see in the for boost and buck boost converter. In this case, in the buck converter, you know that this I out average is equal to your IL average. Okay, so in this case, what happens is you don't need to. So if you limit your I out average, then you are indirectly limiting your IL average. So you don't have to do additional this third step. So this is the first step. So like let's name them. So this is 1, 2, and 3. So this is the first part where we would like to limit our power. So this is our power setting. So you can keep this power as any value you want. So I have kept it like the rated power, but you can make it half the rated power. So let's say you have a power supply and you have 2 knobs to rotate. So in your power supplies, you may have some knobs to rotate and set their power maximum power and the maximum current. So you can consider this as this. So let's say this you rotate to set your power limit, and this you rotate to set your current limit. So you can imagine this as P, and this you can imagine as I. So it can be maximum values or it can be any low value also. Okay, so you set this power limit, and of course you divide with the output average voltage, and then you get some current, some output current. And here, so as I said, in the short circuit, the current can go very high. So we would like to also limit our output current to, let's say, in this example, 1.1 times the rated current. So we will check which one is minimum. Okay, so we'll check which one is minimum, and then so in this case the D is 1. So we have seen that our IL average general expression is, so let me write it here. So our IL average general expression is basically so we have D plus D minus I naught average equal to our IC average, and in steady state we can assume IC average is 0. So we can solve this and we can find this IL average is equal to I naught average over D. Okay, so this is the general expressions, but for buck converter, of course, this is equal to 1. So you may skip this also if you are designing for buck converter, but for other converters, it is important. Then so this way you can convert your output maximum value to the maximum required IL average star or IL average maximum. Okay, and this maximum goes as an upper limit for saturation. So this is your saturation block, and here it will have the upper limit. So this will be your upper limit will be IL max, and then lower limit will be minus IL max. So this decides your saturation limits, and then your control work along with that. So this is very important for protections. So this first thing helps in overload, and the second thing, which is this one, this will help you in short circuit conditions, which we will also see in the simulation results. Okay, so now we have the same thing for boost converter. So it's the same control structure for boost. So you have everything similar. So the only things is going to change is your circuit diagram. So this is your circuit diagram. So this is going to change. Your A value is going to change. So you can see your A value is minus V naught. The B value is your Vs minus V naught average. And your D value is equal to your Vs over V naught. Okay. And yeah, so rest all is exactly same. Okay. And there is one thing I forgot to mention. As I mentioned, the anti-winding thing. So you can see anti-winding here. So when the input and output of saturation is same, so that means there is no saturation. So we give 1 and we use integrator. And when they are not equal, so it means they are saturated. The output signal is saturated. Then we give this 0 and we basically disable the input of integrator. And we would see if we do not do this anti-winding, then how our results are going to look. Okay, so this was for boost converter. And now let's see the short circuit protection and the overload protection for the boost converter. And I have yeah, so let's see this thing first. So it's the same thing which you can see. So this is your first part for protection. So this is for overload. This is your short circuit protection. And this is the thing which I was discussing. So this is your third part. So this is for your inductor protection. Okay, so this inductor protection means the inductor also has some current rating, and we should not allow our currents to go higher than this. And for sure, we find the minimum of all, and then we use that as a saturation limit. So here there is one very important thing I would like to mention, that you cannot protect your boost converter circuit from the short circuit analysis with the same circuit diagram if you have here. So the reason for that is, let's see the circuit diagram in both the mode. So in mode 1, when the switch S1 is on, okay, so mode 1, your S1 is on, S2 is off. So when we have a fault, it would look like this. So this is open, and for sure it is shorted. And mode 2, it would look like this. So let's say this is our VL, and this is our VS. So if you notice, in both the mode, your VL is equal to VS, right? So in both the mode, our VL is basically positive. And we know that if there is average voltage, yeah, so this, so there is a positive average voltage. So what will happen? Your inductor current will keep on rising. And what will be your steady state current? So the steady state current will be decided by the internal resistance of the inductor. So your IL steady state will be basically equal to VS over R, and which is a very high value because this R is very low, because it is an internal resistance of inductor, which is always very low. Okay, so it is a reason we cannot protect our boost converter during the short circuit on the load side. So what we can do to protect our device? So you have to disconnect your DC-DC converter from the load. So when you design your boost converter, I would ask, it will be nice if you also use one switch here. So let's say a contactor, or it can be fuse also. You can add fuse also here, or you can add contactor, and then you can turn on and turn off the contactor. And in case, let's say you have faulted the capacitor, then this contactor does not help. So this contactor helps if you have faulted the low load side. If you have faulted the capacitor, for sure it does not help. So you can also add one fuse here, fuse on the source side, or you can add some contactor also. Okay, so the only way to protect your boost converter is by disconnecting the source, disconnecting the load or the source from the converter. Okay, so this is the same thing for buck boost converter, and here you can clearly see your the A value is is equal to Vs average, B value, Vs average plus V out average. The B is equal to minus V naught average, and D you can see from here. So D is equal to your Vs over Vs plus V naught average. So this is the same expressions which we saw in our presentations also in the beginning. And again, we have the same structure. So this is our circuit diagram. This is the circuit diagram used for buck boost converter. And this is for protection of our inductor and our DC-DC converter during overload and failure conditions. For buck boost converter, it is possible to protect during the short circuit condition because your output of the buck boost converter can be lower than the input voltage, or it can be higher than the input voltage also. So for buck converter and buck boost converter, it is possible to protect them during fault condition, but for boost converter, it is not possible to protect it. Okay, so that was about the Simulink model. Now let's see some results. So here we have the results. These are the step response results and with anti-winding. So we have anti-windings. Okay. So the first column is for buck converter, second column is for boost converter, and the third column is for buck boost converter. And you can see these labels. If you want more time, you can pause this video and see the labels. So the red one is our reference voltage. The blue one is the voltage for continuous time domain, the average voltage, output voltage for continuous time domain, and then this average output voltage for discrete time domain control implementation. And the same thing in the below graph, you can see this is the I out average maximum reference, so which we got from the which we saw the block diagram where we wanted to find the maximum output current for the power limitation and the output current limitation during short circuit. So this is how the reference value changes. You can also see it changes. This is the maximum actually set point for the inductor current, the maximum set point for the output current, and this is for continuous time domain. And then you see this dotted line. So this is again the maximum output current setting for your in discrete time domain. And then this blue curve and the green curve, these are our actual output average currents. Okay, so these are our actual output average current. So the same notation is used for the boost and buck boost converter. And let's see what's happening in what time. So yeah, so this reference value is actually 1000 volt. So you cannot see one here, but I will just write it down. This is your 1000 volt, and for sure you can all see here it is 1000. This is 1000. This is 1200. Okay. And the time also you can see this is 0 time. This is 0.2 second. This is 0.4. This is 0.6, and then this is 0.8 like that. So in the very first beginning, this is your starting of converter. Starting of converter. So we turned on the converter. It was initially 0 volt, and then it went there. So this is a step change. Step load, step V out decrease. Let's say V out decrease. So we decrease from 1000 volt to 800 volts. So to just show you that you can also operate a different voltage reference value. Then we again go back to our 1000 volt reference, and here what has happened? We have increased our load. So this is our overload condition. And you can also see from the current value. So the current value has gone high. So this is the overload condition where we want to draw more power from the DC-DC converter than its rated power. So that's a condition. And then the overload condition is gone. And from 1 second to 1.2 second, this is our short circuit condition. So we have a short circuit on the output voltage. And then again, our short circuit is removed after 1.2 second. So there are many conditions I try to simulate in one Simulink runtime. And yeah, in one Simulink, one simulation, I would say. So you can see that during the overload condition, what is happening? Your first control for limiting your inductor current based on the power calculation. So what happens is this reference value you can see. So the red color, red, blue, green, and then all are overlapping with each other. So that is because of course their output current cannot go greater than the reference or the maximum set value for the output current. And here this I out maximum was computed from the first strategy where we would like to limit our power. And yeah, and then we have load removed, so the current has again come down. Now we have the short circuit. So in short circuit, you can see this is, so our nominal current is 100 ampere, and this is your 1.1 times 100 ampere, so it is 110 ampere. Okay, so this is where your second control is coming into picture. So where we want to limit our current for the short circuit. And here you can clearly see our output currents are limited, and this is only because we have the saturation block for IL average reference value limitation. So for boost converter, you can see your during the overload condition, your output current is limited, and you see little gap in the the maximum and the actual current. So this is because you compute D from the voltage equation. So our voltage equation, so D is basically Vs over V naught. And of course, there are some losses in the converter and non-ideality, so that makes this gap. Okay, but for buck converter, the D is equal to 1, so it does not matter what's the value of D, and so the losses and all will not influence that. And for buck boost converter also, you can see in overload condition, your output current is limited. So for boost converter and buck boost converter, you can see your output currents are limited during overload condition. But here the interesting thing is during the short circuit, you see for boost converter, the green curve and the blue curves are not here. So they are somewhere up. And so, yeah, so so output current is not limited during the short circuit for boost converter, but for buck boost converter, you can see your output current is limited to the reference value, so which is 1.1 times the rated current, so which is 110 ampere. So in buck boost converter, we can limit our output current during the short circuit condition. So this is the graph for step response. So you can pause this graph and pause the video and then look the graph in detail. But let's continue further. And this is the same graph, but this time I try to show you the whole picture. So you see this initial spike for the output current, which is expected. Why it is expected? Because you have the output capacitance and then you have the resistance. So initially it has some voltage. Initially it has the output voltage, and then you short it. Okay. So during the short circuit, you basically short the capacitor. And of course, if you know the operation of capacitor, then you would see that your currents will be very high. If you short the capacitor, then your current will be very high. So this is that moment of shorting the capacitor. But after that, when the energy of capacitor is dissipated, you would see the output current is actually limited to a safe value. So this is the same. This is also true for the buck boost converter. But for the boost converter, as we explained, it's not possible to limit our output current during the short circuit, because during the short circuit, your V out is 0, Vs is some value, and of course your V out Yeah, so V out is 0, which is for sure less than Vs, and this is unstable operation for the boost converter. For stable operation, your V out should be greater than Vs. Okay, so that is your for the boost converter, but this is not true, and hence your boost converter is not stable. And your current goes very high. You can see like 100 ampere, 100 ampere is the nominal current, and you see the currents going around 600, in between 600 and 5, not 600, sorry, 6000 and 5000 ampere. It's pretty huge current. So you cannot let this much current flow through inductor. So you have to shut your converter down. So this is the zoomed section for the step change in the load voltage. So the load voltage has changed from 1000 volt to 800 volt, and you can see the responses. And this is the response which I got it from the equations, from the analytical expressions. So if you recall your third lesson, then you would see command tracking in S domain is basically equal to S into omega 1 plus omega 2 plus omega 1 omega 2 divided by S square plus S into omega 1 plus omega 2 plus omega 1 into omega 2. So you can substitute the value of Kp and Ki in command tracking expressions, and then you get something like this. And I try to give the step I try to get the step response from the Matlab script. So there is a Matlab script also I gave you for the analytical expressions, and I got result like this. And you can see at different instances, your values are matching very closely. So this, yeah. So your values are matching matching nicely with the results, and so it also suggests that our tuning is more accurate. But for buck boost converter, we see little more variation, and yeah, so which is not very apparent here, but in the next graph, this is for step increase, and we can see for boost converter and the buck boost converter, these parameters are not far away. Okay, but for the buck boost converter, we see little variation in our values at different instances. So for example, so at this moment it is expected to have this value, so which is matching. At 0.42 we see it should be 100 and around 112, but it is 104. Still not very far away, but it is actually it is more far away than our buck and boost converter. Okay, so yeah, so you can see these results, but anyway, all the results, these results are acceptable because their performance are nice, and you can see them behaving as expected for all different conditions. Okay, so this is now the command tracking body plot. So this is our frequency domain plot. And as we mentioned in the previous slides, that you can change this variable to 1, and then let the simulation run by the Matlab script, and it will take several hours to, depending on your laptop speed. If your laptop is very good, then you will get results in maybe less than an hour. But for my laptop, it took more than let's say more than 2 hours, I guess. So then I got this result. So this is the body plot for the command tracking plot for buck converter on the first column. The second column is boost converter, and the third column is your buck boost converter. And the first row is your gain, okay, and the second row is your phase plot. And you can see, so these are the parameter settings. So our inner current control loop is tuned for 400 Hertz. Your outer voltage control loop, the second eigenvalue is tuned at 40 Hertz. And you can see, so our bandwidth, the bandwidth of controllers, you can see at different for different topology. And I have just taken few points for the plot, so I do not have many points in between, so I could not give you exact frequency for which you have the value as 0.707, but you can do as many frequency you want to get the accurate value. So this is a second order system, and hence you see this the gain higher than 1. So if it's a first order system, you would and you have tuned it perfectly, then you would not see this this gain greater than 1. But since it is a second order system, you would expect to see this gain as greater than 1. And you can see the bandwidths of the different converters at different frequencies. So the bandwidth of the buck converter seems close to our intent, close to our F2. The second eigenvalue, and the boost converter also, it's not very far away, but the buck boost converter is actually far away. Okay, so this is because of the non-ideality in the converters. And if you get the body, if you want to get the body plot using average circuit diagram, not using actual PWM circuit, then you would see the body plot of all graphs would look similar, and they will be tuned nicely. But since we use the actual circuit, there we have losses and non-idealities, and of course the value of D we have used to compute considering the ideal converter topology. So that also makes some errors in the body plot or in the control tuning. Okay, yeah, but our time domain response are better, and they are acceptable. So this is the same plots, but for different frequency. So you can see the inner current control loop frequency is same, the bandwidth is same, but the outer voltage control loop second eigenvalue is now double. So this time what we have used is we have used F2 is equal to FBR by 5. So not by 10 times less, but it is 5 times less. And you see more overshoot. Okay, so which is expected, because for tuning our outer voltage control for tuning our outer voltage control loop, we assume our inner current control loop gain is 1. And if you do this approximation that your the eigenvalue for the second eigenvalue for the outer voltage control loop is 5 times less, then that approximation is not perfect, and hence you see a little more gain on the converter of the body plot. Okay, so this is the same plot. Now it's enough about presentation. Now we would like to run our Simulink model, and these are the tests we want to do. So the first thing we want to do get the same step response which we saw. Then we would also see this importance of anti-winding, and then how you can get the command tracking plots. So let's do it. So we have already opened our Matlab model and the Simulink model, and if you try to run, then I think you will see some error, because there are these variables which are not defined. So the very first thing you should do is you should go to this Matlab script and check the settings by yourself again, and make this variable 0. If you make this variable 0, so what will happen if you run this Matlab script, you will see all the variables are initialized, but the simulation is not running from the Matlab script. So this is just for initializing the variables, and then you can run this Simulink model, and you will see now the Simulink model should run fine, and you can see your step responses. Okay, so yeah, so this is the same scope, the same picture which we saw in the Matlab during our presentations, and so this is this scope. So you see this big scope. If you open this scope, you will see this graph. Okay, so now so simulation is slower. So I would pause this video, and then once it is about to finish this simulation, then I will again continue. Okay. Now the result is the simulation is over, and you can see it's the same result which we saw on during our presentation. Yeah. So I will not explain this again because it's the same result. And here we have used anti-winding in our system. And now let's see the result. And so before we go there, so you can see this result for the buck converter is looking nice. So it immediately reacts basically when you have when the fault is cleared or the overload is cleared. So you can see during this overload and the fault condition, the error, the voltage error is always positive. So what happens if you do not do anti-winding, your integrator value will keep on increasing, and then it will not immediately react on it, and your results would look I would say worse than this. So let's see for buck converter. Now we do not want to do anti-winding. So what I try to do is I get this fellow out here, then I get a constant block. So I always enable in the integrator. Okay, so let's do that for all the integrators, for the all anti-winding signals. So here you can see my anti-windings are not used. So the integrator is always going to work. And now let's run the simulation again. So again, it is going to take long time. So I would pause the video again, and then we see the result afterward. Okay, so now our simulation is over again. And if you see the voltage expressions for the buck converter, it looks worse than it has the anti-winding. Like without anti-winding, this voltage values looks worse. And you can see that these things are only apparent when you have the overload condition or the short circuit condition for the converter. So as I mentioned, there is error. So there is a permanent voltage error, and this due to this, your integrator accumulates the value, and hence when the overload or the fault is clear, it gives the huge value in the beginning itself. Okay, so since the error is less here, so you see little less spike, which is still actually more, but during the short circuit, the error is huge. It's I would say the maximum error, and then the integrator gives the huge value, and then you get something very high voltage, and then it will slowly come to your the set point. So to avoid these unwanted the transients, we basically use our anti-windings. And you can see for the buck boost converter, so we have anti-winding, and the waveforms are looking much better. Okay, so the buck converter waveform were also better when we had anti-winding. Okay, so let's undo everything. So we will use anti-windings. Okay, fine. There is one more thing I would like to mention, that so here you see this spike in the output current, right? So when the short circuit is there, you see this huge spike in the beginning, and which goes away after some time. But you would not see this spike in the actual converter. So this spike is only because you have shorted the output capacitor. So let's see the buck converter. It's the parameters, not the buck converter, the buck boost converter. And yeah, so if you see this graph, in this graph we have this as output voltage, this is our output currents and the power, and here we have the inductor current. And you can see clearly that inductor current is, we do not see the huge spike in the inductor current. So these are all values at all the operating points, and you can see they are pretty much stable. So your converter does not see that the huge spike, this load current during the initial phase of the short circuit, and this is only because you shorted the output capacitor, and due to that it has a high spike. Okay, so this was about your anti-winding, and now we would like to we would like to see the body plot now, how you can get it. So you can change this variable to 1, and then you run the simulation. You will get your body plot, but as I said, it took a long time for simulation to run. So I would not run for a whole frequency. I will run for just some frequency. So let me choose just some 3 frequencies, so that we get the results quickly. So I just want to show you that. So I just want to show you how this this Matlab script and the Simulink model is working. But for sure, you can do this. You can do the same test for the whole frequency, and you will get the same body plot which I showed you in this graph in the presentation. Okay, so you will get the same body plot after running with for the all frequencies there. Okay, so yeah, so it is going to take again some time. So I'm going to pause video again, and then I'll see you again. Okay, so now the simulation has completed, and you'll once the simulation, all simulations are completed, you will see this scope. And so we just see results for the 3 frequency which we gave. So we gave 10 hertz, 15 hertz, and 20 hertz. And of course, you can give as many frequencies you want, and then it is going to take some time, and you will get your body plot. Yeah. So this was just this I just wanted to do to show you the tool chain. Okay, so now I think I showed you all the results and these 3 points, and feel free to do changes in your Simulink model to try something else. And you can see that we added harmonics in the reference voltage. So we added some sinusoidal waveform, and then your average voltage also tracks the reference voltage, and there will be some phase lag and some gain difference. So yeah, and if you want to see your individual converter and individual control waveforms, then you can also see. And this is for the buck converter in continuous time implementation. You can see your inductor current is changing in a sine wave fashion. Your output voltage is also changing in a sine wave fashion, and your duty cycle is also changing in sine wave fashion. Yeah, so this is one way you can get your body plot. And okay, so this was all about the Simulink model presentation. So now let's see the last slide. So now we have completed the 5 lessons, and so what are the learnings you would have gained after completing all these 5 lessons? So the first thing is you would know the basics of designing your converter controls in continuous time and discrete time domain. So you would know how to get your plant model. Okay, so the importance, the accurate plant model is very important, especially when you want to tune your PI gains to place the closed loop eigenvalues of the system to at desired frequencies. Then we learned how we can tune our PI gain using equations, and how to derive those equations for both continuous and discrete time domain. So we learned 2 methods, like we can do pole zero cancellation, or we place the eigenvalues at 2 different frequencies. Then we learned how we can implement our outer voltage control loop and inner current control loop in cascade form, how we can protect our devices from the fault and overload conditions. Yeah, so this is about protection of our converter during overload and faulty conditions. So this is important. And this you can implement by saturating IL average reference value. Okay. And last but not the least, you know what is the anti-winding and why it should be implemented. So for anti-windings, there are many ways to implement it, and what I have shown is just one very simple anti-winding approach. And this anti-winding is very important, especially when you have the fault or overload conditions. So this is all about this video. I would like to thank you for staying this long with me. And if you like the video and if it is helpful, then please like, subscribe, comment, and share with your friends and colleagues. Thank you very much.